Ever wondered how valuable it would be to predict a dependent variable with more than one independent variable? Let's delve into this thought. In many scenarios, a dependent variable is influenced by more than one independent variable. If we can estimate this relationship, we're in a position to make more precise predictions about the dependent variable than we could using simple linear regression. Welcome to the world of multiple linear regressions. This is an extension of simple linear regression where many of the concepts carry over. For instance, scatterplots, correlation, and the least squares method remain essential components. Suppose we're examining a habitat suitability index for wildlife, influenced by stem density, percentage of conifers, and understory herbaceous matter. By collecting data on these variables and constructing a regression equation, a researcher can answer critical questions about their model and make more accurate predictions. So if we can estimate this relationship, we can make more accurate predictions than with simple linear regression. Let's dive deeper into what multiple linear regression actually is. The general linear regression model is a key component of this process, taking the form of a mathematical equation. This equation includes parameters that need to be estimated based on the sample data. These parameters include variables like the random response variable, its mean value, and the predictor variables. We also have a random error, allowing each response to deviate from the average value. This error is assumed to be independent, have a mean of 0 and a common variance, and is normally distributed. These assumptions might sound familiar, and that's because they are very similar to those for a simple linear regression model with one predictor variable. Much like simple linear regression, verifying the assumptions in multiple linear regression is crucial, and we do this by examining residual plots and normal probability plots for the residuals. Scatterplots and correlation play a crucial role in multiple linear regression. How so? Well, let's begin with scatterplots. They are our first step in visualizing the relationship between the response variable and each predictor variable. Scatterplots help us understand the nature of these relationships, whether they are linear, curved, or even non-existent. Next, it's essential to compute linear correlation coefficients for each pair of variables. This step quantifies the strength and direction of the relationships we saw in the scatterplots. A correlation coefficient close to negative or positive 1 indicates a strong negative or positive linear relationship respectively, while a coefficient close to 0 implies that there's no linear relationship. But what about when we have more than two variables? That's where a correlation matrix comes in handy. This matrix not only shows the relationship between each predictor variable and the response variable, but also the relationship between the predictor variables themselves. It's a comprehensive way to visualize and understand the interplay of variables in our model. Let's wrap up what we've learned about multiple linear regression. It's an essential tool when we're dealing with a dependent variable influenced by more than just one independent variable. By incorporating multiple factors into our model, we can make more accurate and precise predictions. This is a step up from simple linear regression, where we only consider a single factor. However, the complexity doesn't end there. It's also crucial to verify the assumptions of our model. Are the errors independent and normally distributed? Do they have a mean of 0 and a common variance? These are questions we must answer to ensure the validity of our model. And let's not forget the role of scatterplots and correlation. They remain pivotal in visualizing the relationships between variables and identifying trends. They give us a clear picture of how our variables interact with each other. With multiple linear regression, it's not just about predicting a dependent variable. It's about making those predictions as accurate as possible.